that let's make it as interactive as possible. So I give these lectures very briefly, maybe 1.5 hours, to stimulate you. So you need not understand everything what I speak. So what you need to gain from here is what can be done. So how? Okay. So the knowledge what you gain can be implemented at your workplace. That's the purpose. You need not understand everything what I say, but at least you should hear. So okay, something can be done in that line. So that is the objective of this lecture, because so some of the topics that I'm going to cover I teach one semester. Okay, I cannot speak for the entire subject in 1 hour. It is not possible. So we'll make it as short as possible, sweet as possible. Okay, so the topics given to me was very close to my heart, where we take the welding science one step further towards making the final end-use components. But we used to call it as a wire arc additive manufacturing. So that is the name coined by us as welding scientists. So when we used multi-pass welding for creating a final object. But then when we sat in international instrument welding just before COVID, so we standardized the terms for additive manufacturing. So where this technique we now call it as a arc wire DE, arc wire direct deposition. Okay, so the principle is absolutely the same. Where we use welding torch, simple welding torch can be a thick torch or mid torch, where we do pass by pass, continuously we build. It's not a new technique. If you look at the technique of using welding to print an object, the first patent was in 1924. Okay, so by an American scientist. And we used to, when I was doing PhD, we used to call it as weld overlay. And so after we realizing the potential, so we also now use them to print the final end-use objects. Right. So what we are going to see in my lecture, 4 important topics. Briefly, I want to cover. The first one you see here. Okay. So how the automation of the welding processes is going to help us in printing and in realizing the end-use components. So how can we do that? So we may have simple CNC system and robot, but we need to have a fully automated system which you can also make it by a simple means. So how we can make it and why we make it, so that we can print the different components. Right. So and then second topic is one example case study. Recently we successfully implemented in industry, so where we use welding-based additive manufacturing for hybrid manufacturing, combining the conventional way of making parts. And using additive manufacturing to enhance the functional features of the component. Okay, so I'll give you an example of that. Okay, and then 3 science topics. Okay, so how we use the AI and artificial intelligence tools primarily to mitigate the defects that you may see during welding-based additive manufacturing. So one example case study again. Okay, and then 2 more examples. I'll show one on so why conventional welding methodology may not be fully suitable for additive manufacturing. Okay, so you may have to reinvent, or you need to modify the processes so that we can get the defect-free parts and then parts with required properties. Okay, that is what at the end I'm going to show 2 examples. Okay, good. If you have any questions in between, you can also raise your hands, and or you can also discuss at the end. Okay, good. Right. So as I said, the process of using a welding power source, it's not really new. So we've been doing it. In fact, first paper, the journal paper on using a welding deposition, weld deposition for realizing the 3D printed components from India. Okay, the year I was born. Okay, you can guess my age, 1979. Okay, so the place in Trichy. Okay, so one professor gave a talk, and in Trichy, very close to his place where we have DHL. Okay, the Welding Research Institute in 1979, one of IIT Madras, then he became general manager, So he first published in 1979, okay, where he printed, built using a welding-based technique, a complete pipe gland, massive pipe gland, because that time you could not source the pipe. Okay, so he built it layer by layer, okay, massive pipe for one of our power plants in 1979. Okay, so therefore, that time he was not calling as additive manufacturing. For that matter, until 2020, Okay? We were all calling as either weld overlay. Okay? So, or multi-pass deposition. That's what we used to call that. Okay? So later, we also now use that for additive manufacturing. So therefore, it is not new. So what we use here, so we use the conventional, either TIG, okay, tungsten and gas starch, or MIG, okay, metal inert gas. So either you see here, so what we schematically see over there is a TIG setup, or GTAW, in the US they call it, gas tungsten operating setup, with a wire feeding. So we feed the consumable wire, and then subsequently the wire melts and molten metal is transferred, and then subsequently we build layer by layer. Or you can also use a MIG based process where the wire itself, okay, used as an electrode, and then these wire melts by the arc heat, molten metal be deposited. Right, so there are a lot of advantages of this process compared to powder-based processes. Because here we use a very heavy, okay, heat source. You can also melt much more than powder-based processes. So imagine if you use a dual wire, what I showed here, 2 wires, we call it tandem MIG. 2 wires simultaneously we can feed. We create a large molten pool. Okay, so if you use a tandem MIG process, you can build up to 10 kgs per hour, you can build 10 kilograms. So whereas if you use a powder-based processes, so 1 hour you may build hardly 500 to 600 grams max in a powder-based laser-based processes. So therefore, this technique, okay, is best suitable to print large component, large volume components, like printing a propeller, an impeller, okay, or pipe clamps. So probably I'll show some examples later as well. And there are some inherent advantages of this process. Because of the typical process characteristics, it's very simple, right? We need a power source and an motion system. It can be CNC or a robot arm, and we understood the welding science so well, so we can also mitigate the defect. We know how to control the global formation in welding. Okay, so how to avoid undercuts, so how to remove the lack of fusion. So therefore, the knowledge is already available. So we can print really dense solid components with required microstructures, okay, with properties, therefore can be engineered. Right? So that is the simple basic of this process. Right? So what you see here, yeah, one such process. So where we use a tandem MIG source. So this is an high-speed video. So what we see when the tandem MIG process in operation. So you see 2 electrodes are simultaneously fed and we form arc, and then these 2 wires can also be different material, right, or same material. So the advantage of using welding based processes, so we can also mitigate the composition of the molten pool from the dilution. Right, so in this example, image what I showed, so this is an impeller used for a Navy application. Okay, so which we built in collaboration with the University in Australia. So what you see here, this is a part, sorry, sometimes I sound like a music singer. Okay, so yeah, so what you see here, this part, so this we built it for our Navy, where this impeller is rotating very high RPM in a seawater environment. Where the arms see here, so those are all exposed to a very corrosive fluid, right? Seawater. Seawater is one of the most corrosive fluid. And the internal shaft is rotating in very high RPM. So we need to get both high fatigue resistance and corrosion resistance. Right? So conventionally, suppose if you want to make this impeller, it is impossible to produce with multi-material. So we have to make a shaft, machine it out, and then weld each arms, what you see here, okay, individually. Right? So then the weld becomes the weak link over here. So there is this consolidation, you're prone for failure. And this part then we make it with the nickel-based alloys so that the corrosion resistance is achieved. Right? Suppose if you want to use a welding-based system, right? So we can start with the conventional high-strength steel shaft and then start depositing on top of this nickel-based superalloy. But then during this process, we can also vary the composition very smoothly. Suppose if you use a dual wire, we start with an say steel wire deposition and continuously change the nickel concentration during printing such that the composition gradually evolves and it becomes a full nickel-based alloy at the regions where we expect corrosion resistance. So the advantage of using welding-based system here is, so we can print a large component like this, and we can also bring in advantages of functional gradation by changing the composition as and when we print. Right? So therefore this technique becomes very interesting to print large components. And as I said, we used to use this as a prototyping tool in 80s. Look at, right? So this is one of the components first became airborne by using the Arc Additive welding-based system from University of Cranfield. So my academic grandfather's place. Okay, so what you see here is a titanium component, okay, printed for European Space Agency in 1980s itself. So where the deposition was done to print the entire titanium component, and later machine it. We can take it in the airborne application. So now from such a heavy and very niche application, we are also now using this technique, okay, for producing even regular day-to-day components. Right? So what are the materials we use here? So any material that is weldable can also be printed. Okay, that's a thumb rule. So any material, you see that it is weldable. So we can also use that material for multi-pass deposition. So be it low carbon steels, titanium, okay, even magnesium. In fact, magnesium right now I was talking to Professor Siva. So I've been helping him to print magnesium AZ31 alloys as well. Both we can also induce defects to make foam magnesiums, right? Nickel-based alloys. So all these things which alloys have very good weldability, we can also print them. Okay, so